All right, we're back for this lesson. Amazon FSx for Lustre. This is a high-performance file system purpose-built for fast processing of large-scale data sets. It's especially useful in machine learning and high-performance computing. That's HPC environments. But before we get started, hit the like button, subscribe, and share this with anyone who's interested in the AWS Machine Learning Associate exam. So, what is Amazon FSx for Lustre? FSx for Lustre provides a fully managed Lustre file system that delivers sub-millisecond latencies, hundreds of gigabits of throughput, and millions of IOPS. Lustre is a popular open source parallel file system used in many of the world's fastest supercomputers and machine learning clusters. For AI and machine learning applications, EFS serves as a critical infrastructure component that enables collaborative development environments, shared dataset access, and persistent storage for training artifacts. The service supports NFS version 4.0 and NFS version 4.1, these protocols. Right? So it ensures compatibility with the standard Linux-based machine learning frameworks and tools. This shared storage capability is particularly valuable for distributed training scenarios where multiple compute instances need concurrent access to the same training datasets, the model checkpoints, and intermediate results. So EFS operates on a pay-as-you-go pricing model, eliminating the need for upfront capacity provisioning. This approach contrasts with traditional block storage solutions and provides cost efficiency for machine learning workloads where storage requirements can vary dramatically throughout the model development lifecycle. The service automatically handles replication across multiple availability zones, providing both high availability and durability for critical machine learning assets. All right, so why use it? Okay. Performance. Okay. So there's different performance modes. Okay. With this, you have a general purpose mode. Let's see if we can find that. Is it? Let's see. Go back up here. Native. Let's see. Let's expand these all. All right. All right. So general purpose serves the default configuration optimized for latency sensitive applications with IOPS limitations per file. This mode provides the lowest latency per operation and can scale to thousands of concurrent clients. It's well suited for machine learning workloads that prioritize response time over raw throughput, such as interactive development environments and real-time inference services. Then you have max IO mode. This enables higher level of aggregate throughput and operations per second while accepting higher latency per operation. This mode supports virtually unlimited concurrent clients and is ideal for big data analytics, large-scale training jobs, and media processing workflows where maximum parallel access is more important than individual operational latency. Then you have throughput modes. I wish I had brought that up. So there's bursting throughput mode, right? This provides the baseline throughput that scales with the file system size. It offers burst credits for temporary higher performance. The baseline is around 50 megabytes per terabyte of storage, with the ability to burst to 100 megabytes. So this mode works well for applications with predictable I/O patterns and moderate performance requirements. Then there's provision throughput mode. This enables specification of throughput independent of storage size, allowing you to provision exactly the performance level required by your application. This mode supports scenarios where you need consistent high performance regardless of data volume, such as training large neural networks or processing real-time streaming data. Then you have elastic throughput mode. This automatically scales throughput up and down based on workload demands, providing up to 3 gigabits per second for reads and 1 gigabit per second for writes. This mode is ideal for unpredictable machine learning workloads where performance requirements can vary significantly over time, such as research environments or experimentation platforms where usage patterns change frequently. So this would be good for accelerated model training on SageMaker with a large data set stored in S3, or something like genomics, life sciences, video processing, or financial modeling. So some key integrations. All right. SageMaker. Okay, so EFS integrates natively with Amazon SageMaker as a data source for training jobs. It provides an alternative to S3 for scenarios where file system semantics are preferred. This integration requires configuring VPC endpoints and appropriate security groups to enable secure communication between SageMaker training instances and the EFS file system. The integration supports both single instance and distributed training scenarios, with the file system automatically mounted on training instances. This capability enhances or enables use cases like fine-tuning pre-trained models where code and configuration files are stored alongside training data, collaborative development where multiple team members need access to shared data sets and model artifacts, and incremental training where models and checkpoints are continuously updated. Okay. So you can see this walks you through. Save this, or you can search for it. Just look for SageMaker with EFS. Then you also have container and Kubernetes support. All right. So EFS provides excellent support for containerized machine learning workloads through integration with Amazon ECS and Amazon EKS. Containers can mount EFS file systems as persistent volumes, enabling stateful machine learning applications that require shared storage across container lifecycle events. For Kubernetes-based machine learning pipelines, EFS supports both static and dynamic volume provisioning through the Amazon EFS CSI driver. This integration enables sophisticated machine learning orchestration scenarios where training jobs, feature engineering pipelines, and model serving applications share common data sets and artifacts through persistent volumes. Then, serverless compute. I don't have a good image for that, but this one is, yeah, save this, but serverless compute. So with Lambda functions, these can mount EFS file systems and enable serverless machine learning where functions need access to large models, shared libraries, or cached data. This capability supports use cases like serverless inference, where model artifacts are stored in EFS, data pre-processing functions that can access shared data sets, and trigger-based machine learning pipelines that process data as it arrives. The serverless integration eliminates the need to package large machine learning libraries or models with Lambda functions, so it reduces the deployment package size and enables more flexible serverless architecture for machine learning applications. So there's three major services that work with this. There would be the S3, which would be optional data repository for FSX. So the data is lazy loaded or burst transferred. Then there's SageMaker, so where you can mount FSX as a fast local file system to training jobs. And then you have the EC2 ECS, where you can use FSX as a shared high performance volume. Okay. You can see more information on how this would be deployed. Okay. That's not where I wanted to go. Well, let's do a little bit of pricing. Okay. Yeah, let me see if I can find one. Fsx Lustre pricing. Okay. I thought I had one up here. My apologies. Yeah, okay. So EFS pricing consists of several components that affect total costs. Storage costs can vary by storage class, with standard storage priced higher than infrequent access and archive classes. Throughput costs apply when using provision throughput mode based on the amount of throughput provisioned beyond the baseline. And request costs apply to certain operations, particularly for files stored in infrequent access and archive classes. Data transfer costs may apply for cross-region replication and access from other AWS services. Understanding these cost components is crucial for optimizing machine learning workloads, as storage patterns in machine learning often involve large data sets with various access patterns over time. And then you have cost optimization best practices. So when you implement an appropriate lifecycle policy, this can dramatically reduce your storage costs for machine learning workloads. You need to consider transitioning data sets, particularly training data sets, to infrequent access storage after model training is completed. Then you can move the archive model versions to archival storage for long-term retention, and you could use one zone storage for development and testing environments where high availability isn't required. For compute optimization, consider using elastic throughput, for variable workloads to avoid paying unused provision capacity. And then you can monitor the actual throughput, use usage patterns, and adjust provision throughput accordingly if using provision mode. And you can implement proper data management practices to avoid storing unnecessary duplicate data sets or intermediate files that can be regenerated. So yeah, so basically pricing is based on storage type, throughput, and deployment type. And you can see the tiers and the cost here. All right. All right. Let's go to the next section. I think we'll do performance tuning. Yeah. Okay. So performance tuning, there's a couple of components, right? First, you have optimizing the training performance. For machine learning, training workloads often involves sequential access to large data sets, which EFS can optimize through proper configuration. Using general purpose mode provides the lowest latency for small random input-output operations, and it's common in data loading. While max IO mode may be beneficial for large parallel training jobs and can tolerate higher latency in exchange for higher aggregate throughput. Consider the data access patterns of your machine learning frameworks when you consider configuring EFS. Something like TensorFlow, PyTorch, these data loaders can benefit from parallel data loading across multiple workers, which EFS supports through its concurrent access capabilities. And implementing proper prefetching and caching strategies at the application level can further improve the training performance. All right, then you have number 2, optimizing for inference performance. So model inference services typically require low latency access to model artifacts and may benefit from keeping frequently accessed models in standard storage while archiving older model versions. The concurrent access capabilities of EFS enables multiple inference instances to share the same model artifacts without duplication, reducing storage costs and deployment complexity. For high throughput inference scenarios, consider using provision throughput mode to ensure consistent performance levels regardless of file system size. Monitor inference latency metrics to ensure the storage performance isn't becoming a bottleneck in your machine learning serving pipeline. So let's go through a little bit of what this would look like in the console. Let's see, Fsx. All right. All right, we got the Fsx. Okay, so this is a fully managed service, so it does have a little bit more cost. But when you go here, all right, or you could do the little dice, which I think would be under storage. Yeah, storage Fsx. Okay, so most people don't typically use this, but we're going to try and walk through this because I don't really use it. Okay, so at the console, let's create the file system. Then we can begin to configure the process, right? So we can choose any of these, right? You do the NetApp on tap, OpenZFSS, Windows File Server, or for Lustre, right? We're gonna go for this. Okay, then we go for basic settings, right? So let's see. Fsx test. 0.4 terabytes. All right, we want the persistent, intelligent tiering, the throughput. You can go very high, right? But let's stay pretty low. IOPS, the metadata configure. Oh, yeah, that's fine. Data compression type, cluster version. This is using the default VPC, which is not recommended. You should have a separate one. Security groups that we spoke about earlier, appropriate subnetting, and the encryption, where you can enter one that you've already created. Then you have a bunch of different optional fields as well. Okay. Data repository. So this would pick up from the file system or S3, import the metadata from this. And then what are the input settings that you're having here, right? Which updates, choose which updates on the data repo should be propagated. Okay. The export settings. Then you have your logging. Where's that going to log to for CloudWatch? Boom. And it's going to cost a little bit more. And then your backup and maintenance. How are you going to have this set up? Automated. When it's going to go. Oops. Sorry, that was not meant to be pressed. Or you're going to the weekly maintenance window. So you can basically do a daily, an hourly, and a weekly, right? Very solid. The root squash. Now, I am not too sure about the root user can access the file system. Okay, so this would be the root. This would be your Linux basic setup. What root do you want to have in the Unix? So I don't know, 3, 1000, something like that. Uh, you can client address. We don't need this though, since we're not going to complete it. Then you can add your tags, right? Your environment, your contact, you go on to your project, your team, cost center, et cetera, et cetera, et cetera. All right. Next, you see all this that we've selected, what's editable, what's not, what the values are, what the attributes are. And then you create the file system. Okay. We're not going to do that because this is going to start costing. And then you could do the lifecycle management, um, any transition rules, any security groups that you need to configure. And you could mount this once completed onto an EC2, right? And then from there, you could install your Amazon packages, your mount points, and the file. Then you mount the file system, excuse me. All right. And then let's go into SageMaker. All right. All right. So this integrates with SageMaker with a couple of different pieces that I'm going to point to, but we'll go see SageMaker. We're not going to go in there into the studio. So one thing, first things first, you need a VPC, always useful, right? You want a very specific VPC. I only have the default here. Okay. Second, you would like, what am I not seeing? An endpoint. All right. So you get the endpoint attached to the VPC. You have that interface VPC endpoint for the EFS in the VPC, and then it enables secure communication with SageMaker, which we just showed. And then you would want to set up a security group. All right. So you have that endpoint you created. You have the security group you're going to create. The security group allows the communication between SageMaker and the SageMaker training instances and the EFS mount targets. Security group, right? And then that's pretty repetitive. So in SageMaker, all right, let's see. SageMaker. It's probably going to documentation. Oh, no, it's not. That's good. Okay, so for SageMaker, you would get a training job. Um, Why am I not seeing this? Out there, training job, right? So you'd use this training job. When you create this, you could specify the EFS as a data source and use the file system ID and the mount path that we were speaking about. And then once it's connected, you test the integration by running a simple training job that reads the data from the mounted EFS file system. So what was that in order? You need the EFS system, the FSX, right? You create that file system. You select all your throughput, IOPS, all of that. You create it. Then you create your EC2. Then you create your VPC. Then you create your security group. Then you create your endpoints. And then you create your training job. And at that point, you would have a, a solid best practice, secure, high throughput, high input output SageMaker and data pipeline. Okay. So the best practices for this would be when you're using FSX and SageMaker, S3 is always good because the downloads are solid, but they do limit model training. If you mount FSX in read-only mode, when sharing data sets, there is an increase in what you can do, and you should pre-cache frequently used data sets for any training you're going to do. There's also a couple of other areas we could focus on, but that was an overview. Let's see if I can find the. Yeah, this would be very useful in the Amazon documentation. Let me see what else. No, pricing, already getting over that. Optimizations, performance, we went over that. Performance on nodes. Uh, um, Storage consumption. That might be good. Hmm. You know what? Okay, we'll do this. Okay, so optimizing it. So there's different data organization strategies, right? So when you organize your EFS file system structure, you need to do this to support efficient machine workflows. So you need to create separate directories for raw data sets, process data, model artifacts, and experimental results. This would facilitate lifecycle management and access control while making it easier for team members to locate and use shared resources. When you implement naming conventions that include the version information, the timestamps, and the ownership details, you avoid conflicts in the collaborative environments, similar to how we would use tags for our resources, but for different functionality. Um, Different, but somewhat similar functionality. All right. And then you can consider using symbolic links to create stable paths for frequently accessed data sets while allowing underlying data to be moved between storage classes. Um, let's close this. Let's close this. Okay, performance monitoring. Yeah. Okay, so monitoring EFS performance is done through CloudWatch. With this, you can identify bottlenecks and optimization opportunities. And the key metrics include the total I/O time, the throughput utilization, and client connections. You can set up alerts for performance degradation that might impact the machine learning training or inference operations. And then with this, you can use CloudWatch Insights to analyze access patterns and identify opportunities for cost optimization through lifecycle policies. And you can monitor the balance between performance and cost to ensure that your EFS configuration remains optimal as your machine learning workload evolves. Okay. And finally, yeah, this will be good. Okay, backups. We touched on that briefly when we were configuring that with the daily, was it hourly, daily, weekly. Okay, so you can implement automated backup policies to protect the critical machine learning assets stored in EFS. And then you can also do AWS backup, which provides a centralized backup management for your EFS file systems, enabling a point-in-time recovery and a cross-region backup replication for disaster recovery scenarios. So consider implementing the cross-region replication for critical data sets and model artifacts that support business critical machine learning applications. So this strategy will provide protection against regional outages and enables geographical distribution of machine learning workloads. So that is what I have for this. I think it's a good overview. Um, I think the next one we're going to do will be determined. But I hope you enjoyed this, and hopefully you'll come back for the next lesson. Anyways, before you go, remember to click the like button, subscribe, and share it with anyone you know who's taking the AWS Machine Learning Associate exam. Have a good day.